In this lesson, we're going to start graphing polynomial functions. We're going to build on everything we've already learned and explored. So your essential question is, how do you determine end behavior and use it to graph polynomial functions? We had the opportunity to explore polynomial graphs in Desmos in class. And I'd like you to go down to what you decided or what you summarized for end behavior. And hopefully you realize that the end behavior of an even degree polynomial will always go in the same direction, and the end behavior of an odd degree polynomial will always go in opposite directions. And we're going to summarize that a bit more, and we'll use the end behavior notation today. Also in this table, this was another way for you to think about, well, if it's an even degree, but my leading coefficient is either negative or positive, what does that look like? And if it's an odd degree and my leading coefficient is either negative or positive, what does that look like? And I'll actually put that into words for you today. So the end behavior of a polynomial functions graph is the behavior of the graph as x approaches infinity or negative infinity. So we look at the outputs as x is going in different directions. And I made a table very similar to the one that maybe you summarized in Desmos. And first of all, let's talk about even degree functions. So possibly a really familiar even degree polynomial function might be a parabola. And a parabola, as you know, would have a parent equation of y equals x squared. So if I have y equals x squared or any even degree polynomial, the end behavior looks very similar to this as long as the leading coefficient, or my a, is positive. So if I have a positive leading coefficient, I know that my end behavior can be described like this down here, where if x is getting really large, y, or f of x, is also getting really large. However, if x is getting really small, y, or f of x, is still getting really large. And a perfect example for that would be your parabola. With a positive coefficient, as x is getting really large, so is y. And as x is getting really small, so as we move from the origin and head to really small values of x, y is still getting very large. Now notice the end behavior here for a positive leading coefficient and even degree, they're both going up, right? They're both going the exact same direction, but they're also both going up. Now what happens if we change that and we make it a negative leading coefficient? So one that you would be familiar with of that would be a parabola, still the parent graph y equals x squared, but facing down. So we would make that y equals negative x squared, where a is negative 1. And again, you're very familiar with this function, I hope, and how it's graphed. So as x is getting really large, y is going down, getting really small. And as x is getting really small, y is also getting really small. So then we can say that the end behavior is described down here as x gets large or goes to infinity, f of x gets really small or goes to negative infinity. And as x gets really small, f of x still gets really small. So you can see that those end behaviors are the same, going in the same direction. So for an even degree, whether it's a positive or a negative leading coefficient, you're going to have end behavior going in the same direction. Well, what about the odd degree? So an odd degree polynomial, what I'd like you to think about when you think about an odd degree polynomial, and this one's a little bit newer to you, but I'd like you to think about the parent function y equals x cubed. So what we have seen about y equals x cubed so far, And this is, you know, the constant is 0, so we know that we have a y-intercept of 0. And there's no other terms. And we know that as x gets really large, this function goes up. And y gets really large. However, as x gets really small, this function has smaller and smaller and smaller outputs. Okay, so this function kind of looks like a curve that goes through the origin, however, kind of flattens out at its y-intercept at 0, 0. So notice that end behavior, when you've got a positive leading coefficient, as x gets large, f of x is getting large, and as x gets really small, f of x is getting really small. So now our end behavior for our outputs are going in opposite directions. And that's going to be the same with this negative leading coefficient. The only difference is now, if I graph y equals negative x cubed, well, the positive outputs that were on the y equals x cubed, those now get reflected in the x-axis. So those positive outputs that I used to have now come down here. They are reflected in the x-axis, and all of those negative outputs that I used to have now get reflected in the x-axis as well. And again, it goes through the origin, it flattens out. And so your end behavior can be written like this, right? As x gets really large, what's happening to f of x? Well, it's going down, it's getting really small. And as x gets really small, f of x is getting really large. So you can see once again, anytime I have an odd degree polynomial function, the outputs always go in the opposite direction. So these go in the opposite direction. So let's use that information to describe the end behavior using the end behavior notation for the following problems. So y equals x squared. Well, hopefully we're super familiar with this one by now, but this is how we would go about figuring this out. We're going to say to ourselves, well, let's start with the degree. We know it's an even degree. So we know that the end behavior goes in the same direction. Okay, and we also know that our leading coefficient, our a, is positive. It's greater than 0. So we are going to be dealing with this example here, the top left corner, where as x goes to infinity, f of x goes to infinity. And because the end behaviors are exactly the same, when x gets small, or as x goes to negative infinity, f of x will still be going up and getting larger. So that's how you describe end behavior. So this is me describing end behavior. The top is just me kind of summarizing what's happening. All right, so let's look at B. So for B, we know that we have an odd degree, which means that our end behavior will be in the opposite direction. And we know that A is positive, or that our leading coefficient is positive. Okay, so that means on the left side, or as x gets really small, f of x will be getting really small. And it also means that as x gets really big, f of x will be getting really big. So it's this top right cell. So we can write, and I always start off going in the positive x direction. You can change these around. I also always start off with x, but you can also start off with f of x. So as x gets really, really large, we know that f of x gets large. But as x gets small or goes to negative infinity, so does f of x. Opposite end behavior. All right, well, how about C? Okay, so this time we've got an even degree. However, our leading coefficient is -5, so we know that it is a negative leading coefficient or less than 0. Well, we still know that our end behavior is going to be in opposite direction, well, we still know that our end behavior is going to be in the same direction because we have an even degree, but that A being negative means that it's reflected in the x-axis. So both sides are going to have negative outputs, getting really, 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 really small. So as x gets big, f of x goes to negative infinity. And as x gets small, or goes to negative infinity, f of x still goes down to negative infinity, or gets small. So there's our description. All right, so now we've got an odd degree. Okay, and we have our leading coefficient is negative again. Well, we know if it's odd degree, it's going to have an opposite direction end behavior. And this time it's going to be up on the left and down on the right. So we can say as x gets big or goes to infinity, f of x goes to negative infinity. And if it helps you, maybe, if you need to see a little drawing, you can kind of do that. So I know that as x gets big, or that direction, right, we're going down. So f of x is getting negative. And as x gets small, or goes to negative infinity, then we know that f of x this time is going to positive infinity, or getting large. Now let's use that information to kind of help us graph these. These are not going to be perfect graphs. These are going to be enough of a graph to get the gist of what this thing looks like. You'll use a little bit more information that you know, but right now you're not going to be able to find all the x-intercepts. You're not going to be able to find all the critical points, and that's okay. Let's just do the best that we can to graph this using end behavior. We'll use our constant to help us find our y-intercept. We'll think about how many roots this thing should have, and maybe how many critical points this thing should have, based on our exploration that we did in class in Desmos. All right, so first of all, I look at this function and I identify the end behavior. So let's talk about that first. So always start there. First of all, end behavior. Well, it's odd. And we also know that our leading coefficient is positive, which means it must go down on the left and up on the right. I also know the y-intercept. My y-intercept is the same as whatever my constant is. And my constant here is -1. So my y-intercept is 0, -1. I can identify other things. Well, because it's a cubic, at most, I know that I could have a max of maybe 3 roots, a max of maybe 2 critical points, and a max of maybe 1 point of inflection. Okay, that's the maximum. So if you ended up with like 4 roots, you'd know that there would be a problem. All right, so I'm going to go ahead and I'm going to graph my y-intercept. So I know that 0, -1 is definitely a point on here. Other than that, I'm going to go and make an input-output table. That's the best that I can do right now. You're going to learn a lot of other tools. And for this one, I'll have us start at -3, -2, -1. Now, we already know what it is at 0, so I'll just skip that. And how about 1, 2, and 3? Okay, and I did all of this math for us so that way we could go through and make sure that this video didn't take forever. Okay, so if I plug -3 into this function, I end up getting a -7. If I plug, and hopefully by this point, I'm just doing direct substitution. You could also use synthetic substitution to do that. Totally up to you. If I plug -2 in, I'm going to get 3. If I plug -1 in, I'm going to get 3. If I plug 1 in, I'm going to get -3. Plug 2 in, you get positive. Plug 2 in, you get +3. And plug 3 in, and you get 23. Okay, I'm just going to plot these points, but I have a general understanding of what this graph looks like. And that's the really important part. Because I know that my end behavior needs to take on a certain form. So at -3, I'm down at -7. So let's see. This will be -3. This will be -7. Now at -2, I'm up at 3. And that's weird because at -1, I'm also up at 3. Okay, we'll have to come back and think about that. Then I'm back down below the x-axis for my y-intercept. Let's see, then at 1, I'm still down at -3. At 2 now, I'm back up above the x-axis at +3. And at 3, I'm way up there, way the heck up here somewhere at 23. Now, again, we know that a maximum of 3 roots is going to happen. And I'll tell you right now, because this has all of its terms, right, they go in order. So I go from an x cubed to an x squared to an x to the first to an x to the 0. This is going to have all of those roots. You're going to have 3 roots, okay? And so the best guess we can make is that because it's down on the left and up on the right, there's probably going to be a higher point somewhere between -2 and -1. There's probably going to be some higher point up here. So it's probably going to go above and come back down so that way it can come down, hit the y-intercept, turn back around somewhere, go back across the x-axis. So what I'm saying is it's probably going to look something like this. And I'm going to do my best job to draw this. So maybe it looks, we know it takes off after probably 323, and I'm not even going to be able to get all the way up to 323. But this is about what that graph is going to look like. Now, again, you don't know how to find your x-intercepts right now. Don't worry about it. It's not going to be perfect, but we have some good points. I've got the end behavior, I've got my y-intercept, and I've got several points. Now, I know that I can have a maximum of 2 critical points. This actually does have my graph, even though they're not perfect, right? I have a couple of critical points. And I know I can have a max of 1 point of inflection. Well, I can see that the graph goes from concave down to concave up. So my point of inflection is somewhere between there. So again, just looking at end behavior, really getting an understanding of what this graph is going to look like, but maybe not the most perfect graph. So let's start with end behavior. So I know that this is an even degree. So how about I start here? Always start with that. So I've got its even degree, and I've got a leading coefficient that's negative. So that tells me that it's going to go down on both sides. I also know my y-intercept. My y-intercept, well, I don't see a constant here, so there's really a +0. So my y-intercept is at 0, 0. also the things that I know about a fourth degree function. I know that I can have a max of 4 roots. I know that I can have a max of 3 critical points. And I know that I can have a max of 2 points of inflection. So that should give me a really good understanding. Now, it doesn't mean I need to have all 4 roots. However, because every single term is accounted for, so I have an x to the 4th, then an x to the 3rd, then an x squared, then an x to the 1st, right? Then my constant 0. But because I have every single term in between x to the 4th and my constant, I'm probably going to reach those 4 maximum roots. That differs from like C. So when we get to C, we're not going to get our 5 maximum roots, okay? And that's going to take a little bit of experience for you to see. Now, once again, I went through and I made an input-output table. Called this one R of X. And I put in -3, -2, -1. I didn't have to put 0 in because I already did that. 1 and then 2. I got to 2 and I realized, hey, 2 is going to -16. That's already off my graph, so I stopped there. Plugged in 1 and I got 3. Plugged in -1, I got -1. Plugged in -2, I got 0. Oh, so I did get a root. That was lucky me. Plugged in -3, I got -21. So I have a couple points really off this graph, which is telling me that this is, decreasing quite quickly. So let's see here. 1, 2. -3 is way off the graph. I'm at -2, I'm at 0. That's cool. -1, I'm at -1. At 0, 0, I have my y-intercept. 1, 3. See, that's 3. And at 2, I'm already off the graph again. All right, so I'm going to start at my lowest point on the left. I'm going to come up through my root at -2, 0. I'm going to circle back, come down. Then I probably need to get back to my y-intercept, so I'm going to circle back again, go up maybe to this 1, 3, and come back down. Maybe something like that. Now this is, again, not going to be the most perfect graph, okay? I'm making some educated guesses based on what I know about this graph due to the fact that I know its degree. I explored some information about roots, critical points, and points of inflection. Okay, so the end behavior matches what I believe the end behavior to be, right? I think it should be down on both sides. Good enough graph for this point in our education. We will get more specific as time goes on. So we've already talked about the fact that it's probably not going to have 5 roots, but it could have a maximum of 5 roots. Let me start with end behavior. So we know that this is an odd degree and A is greater than 0. So it's going to be down on the left, up on the right. I also know my y-intercept. My y-intercept is the constant here, which is at 0, 2. I also know that I can have a max of 5 roots. However, because we don't have all the terms from x to the 5th to x to the 0, you're not going to end up with those 5 roots. I know that I can then have a max of 4 critical points and a max of 3 points of inflection. Those are not going to happen because you only have the 2 terms. Okay, so once again, we'll make an input-output table. At this point, that's what you're doing. You can use, again, direct substitution, or you can use synthetic substitution to help you out. When I did it, I used -3, -2, -1, 1, and 2. So when I plugged in -3, I got -241. That was pretty darn negative. When I plugged in -2, I got -30. I probably didn't even need to use that -3. Okay, this thing is decreasing very rapidly as we go to the left, as x gets small. Okay, at -1, I got a +1. At 1, I have 3. And at 2, I'm off the charts at 34. So on the left-hand side, let's see. -3, I'm not even going to worry about. -2 is way the heck down here. Okay, it's off the chart. At -1, I'm at +1 here. I know that my y-intercept is at 0, 2. Let's see, I've also got 1, 3. And 2, 34, way off the charts. So now, if you didn't know anything about this graph, you would not know how to graph this. You would not know, and you would look at this and you'd be like, well, maybe it's a line. Well, it's not a line, right? It's a polynomial function to the 5th degree. This is going to look a lot like a cubic function. You're not going to end up with those maximum of 5 roots. Really, you're just going to have the 1 root. Okay, so this graph is going to come up. It's going to look a lot like a cubic. It's going to come up, kind of flatten out, and head back up. It's going to look something like that. All right, our last example is a word problem. So we're dealing with some rainbow trout. Yum. And they can grow up to 40 inches in length. And the weight in pounds of a rainbow trout is related to its length in inches. And they have given us a model. Somebody figured out this model, that's the relationship between the weight of a rainbow trout and its length. We're going to graph the model. We're going to actually use a graphing calculator. But before we do that, let's make some sense out of our axes. Okay, so my vertical axis is going to be the weight. And we're going to let that be in pounds. And my horizontal axis is going to be the length. Actually, let me write this because I've got L for pounds, L for length. So let's make sure we got the length. And length is going to be in inches. Okay, so let's start by graphing this and getting an understanding. And let's think about a rainbow trout. Do I want any negative inches? Can you ever have a negative length of a rainbow trout? No. So I don't care about anything besides the first quadrant. So when I graph this in my graphing calculator, you care that it can get up to 40 inches in length, but you don't care that it can have any negative length. Okay, so there's my function, and I'm going to adjust my window. So we said that the most that it could be would be 40 inches. So why don't I make this 50 inches? I'm not sure how much a rainbow trout could weigh, but why don't we say 50 pounds? Now, does this look like a polynomial function to you? If you're struggling to see this as a cubic function, let me just show you. You don't have to do this at all, but if I went to my x-min and I put in maybe -50 there, and my y-min and I put in -50 there, right? It looks more like a cubic function now. I'll go back and change my window the way that I had it. So really my graph looks something like this. Now remember, when the trout is 0 inches in length, it weighs nothing. But as it starts to increase, like ½ an inch, it becomes a little bit larger, right? Until it starts to grow like that. Okay, and that just happens to be, right, half, the positive half, basically from here on, of a cubic function. Now the question is, use your graph to estimate the length of a 10-pound rainbow trout. We are not estimating anything. We're going to actually find the exact weight based on this model. So if I know that the weight is equal to this function, and I'm looking for the length of a 10-pound rainbow trout, well, for weight, I could plug in 10. Now, in the future, we're going to learn how to solve this algebraically, but for now, you know how to graph this. We'll put 10 in y2, because we've already got this in y1. And then we'll figure out their point of intersection. And that'll be how long that trout is. Now I'll figure out where they intersect. I'll go to the left, go to the right. My calculator works a little bit differently than yours. It's going to go ahead and give me that intersection at 27.144. So this point right here is 27.144, comma 10, which tells me that the length of a 10-pound rainbow trout is approximately 27.144 inches.